All right, good afternoon, chemists. Woo, that is way too loud. Okay, all right, good afternoon, chemists. Welcome to Chemistry 1250 with me, Dr. Wynn, or Dr. N. A lot of students just call me Dr. N because there's a lot of silent letters in my name. So today's lecture will be 80 minutes. I anticipate to spend about 20 of it going over syllabus, course logistics stuff, so we all hit the ground running this semester for this course, and then we're going to jump right into chapter 1. So I just want to make sure everyone understands how this course is going to operate. I want you to be fully aware of where to get resources, especially in case you have to miss or if you fall behind. All of the resources I provide to students are available to everyone. So I want you to know where they are in case you're struggling, so you know where to get that help. And then hopefully I'll make sure that we have enough time to blow some stuff up, all right? Okay, great. Okay, so I'm gonna go through like 12 course logistics slides. So your first question might be, well, where do I find these slides? I will show you. All right, so everything important on this class is on our course modules. So for lecture, I post all of our lecture material under a specific course module. Oh, thankfully, someone in the front row, you're in the splash zone. That was a joke. Okay, yeah. Yeah. So I post everything, and the lab team posts everything in modules. So this is where you want to work through. So you see there's a start of term tasks here. We want you to work sequentially through all of these. If you work through all of these sequentially, you will get registered for lab. You'll get registered for online homework in the appropriate way using your Carmen Books fee if you go through these start of term tasks. Now everything else, after a week or so, we'll get rid of that once we get rolling. But what you see here are our lecture resources. So I have how to register for online homework, the textbook link, all of that stuff. I put it up here because we're all registering at the same time. But what I want you to look at here under the lecture resources is where we get our slides for our day-to-day lecture classes. So down here, you'll see we have a chapter 1 page. And what to expect for this class is that every chapter will have its own page. We cover 13 chapters, so how many chapter pages will there be? 13, very good. And so this is what you expect on every chapter page. So for chapter 1, you will find the exact same lecture slides I am going through right now. I post lecture slides 2 different ways, 1 slide per page and 2 slides per page. I am a 2 slides per page girl, but you figure out what works best for you. I like it portrait style and 2 slides per page. So you figure out what you like best, send it to your device or print it out, whatever you want. I link online homework here as well for your just easy access, but you'll also see it in our Carmen assignments. If you go straight to the OWL website, you'll see them all there, but I have them listed here as well. And then I have additional resources for that specific chapter. So you see here I have a printed periodic table, some fun stuff. I also have extra practice problems if the problems that we do in class aren't enough for you. And so what makes this resource valuable is not only are there practice problems like there are at the end of the book, but I also have very detailed worked out keys for every single one of these chapters and usually additional explanations for all of them. So one of the reasons I was so successful in undergrad, or at least I think so, was because I made sure that I had access to solutions manuals, meaning I essentially just purchased all the solutions manuals to my textbooks in undergrad, so I had those answers as I was studying for my courses. And so I've extended that to my own courses that I teach. I want everyone to have access to that, to make those solutions manuals more accessible to students, all right? Students are more likely to do practice problems if they can have the answer and someone essentially holding their hand to guide them to the answer right in front of them. And so that's how I encourage students to pick up a pen and do more practice problems. So every chapter will have that. Okay, so that's where you get chapter 1 slides, so grab those. And then also grab the intro slides that I have here as well, and we'll go through them. But what you see, everything is organized by modules here. We have an SLDS module, and then lab has its own module too. Okay, so let's go through these logistics slides. Okay, so a little bit about me. I already introduced myself, Dr. Lisa Wynn. I've been teaching here at main campus for like 3 or 4 years now. I've taught at least 5 or 6 sections of Chem 1210 and 1220, but 1250, Chemistry for Engineers, is kind of my new baby class. All right, this is my class. I'm the only person who teaches this course, and you guys are my second cohort of engineers to fall under my domain. So last year I taught Chemistry 1220, but it was in a smaller section. It was only 50 students, but we had a really great time. I was able to expand the class to a larger room like this and get it into McPherson 1000. McPherson 1000 is one of my favorite places on earth. I don't know, I just love it here. I teach in this classroom 3 times in a day. This is the 3rd class I've taught today. I'm literally going crazy. All right, but I already started off crazy. So that's a little bit about this class structure, all right? So I will point out any stories that you've heard about Chem 1250, they're just not true anymore. I've only taught this course one other time. And the likelihood that you are talking to one of those 50 people who took my class, I got really positive SCIs, all right, from 1250. I'll tell you, it was a 4.87. Okay, on my SCIs for 1250 last year. So I'm just saying, if someone's like, oh, 1250 is hell, I mean, chemistry is hell, okay? And so if you want to have an interesting person to listen to for 80 minutes 2 times a day, then 1250 with me is not so bad of a deal, all right? So I'll just keep that in mind if you hear horror stories. I'm here to support you all. I have tons of resources to help all students find success at the end of the semester. All right, I didn't discuss my dream board yet. All right, so here's my dream board. I was named after Lisa Simpson. My brothers named me. Do I have her personality? I don't know. So every morning I drive here to campus from my hobby farm over on the east side of the state near Buckeye Lake in the great old county of Perry County, where there's actually more people at OSU than in the entire county that I live in. So I live on what I call my hobby farm with my 2 cats, my 9 chicken and ducks, and my 1 husband. All right, so every morning I get up at 5 a.m. to feed and water the ducks, make sure that they're happy before coming into class, into campus to teach some eager minds. So I, again, live on a hobby farm. Me and my husband have lots of projects where I think our chemistry background is really, really useful. I feel like on a day-to-day basis, I act more like an engineer, maybe because I'm like lazy and cheap also. I like to think of myself as a redneck engineer at heart. And so I feel like the chemistry concepts I learned in my undergrad are really instrumental to my everyday life. And so I hope to bring those values and bring those skills into this classroom, and I've designed this class as such. So that's a big part of my philosophy. There are my cats, there are my chickens. I think all of them are alive at the moment. And then I mentioned that McPherson is one of my most favorite places on earth. I think number 1 is my home. It's my favorite place to be. Next would be Disney World is my favorite place to be, because Disney is a great place to be as single adults. We're called DINKs, dual income, no kids. It's great to go to Disney World as adults. There's plenty of food, drinks. It's just great when you have no kids to wrangle around. So Disney is what did I say? Number 2? Disney's number 2, and number 3 is Costco. It's my 3rd favorite place on earth, and then number 4 is this classroom, McPherson 1000. All right, with all of you guys. All right. Okay, so that's about me. Come hang out with me in office hours, and you can learn more about me and this class, and not only get help, but we can just talk about cool things. I have a student from 1250 who comes to talk to me about engines, cars. He works on Porsches all the time, and I pretend like I know what he's talking about. All right. So what is this class logistically? So expect every week we'll have lectures, 2 lectures with me in this room for 80 minutes. We'll have 1 or 2 homework sets per chapter. Each chapter will have about 1 to 2 hours of online homework. I'll make sure I announce those due dates. They also appear in your Carmen calendar, and you'll have a 1-hour lab with your teaching assistant every week, except we don't have any labs this first week. We have 3 out-of-class midterms. We're going to have 4 5-ish group projects, and then we're going to have 1 cumulative final exam at the end of the year. All right, so that's what to expect. So if you talk to other folks in Gen Chem, chemistry, for engineers, so 1250 is the only Gen Chem class that does not have a recitation, all right, just so you know. So we don't have that. So the grading scheme for this class, it's broken up like this. Each of our midterm exams is worth 13% of your grade. Your final is worth 20. Lab is also worth 20% of your grade, and kind of these lower I guess, lower stress level assignments, online homework, and these group projects. They're meant to be low stress environments for you to earn points. So one of them's online homework. The other ones are these group projects, which we'll talk about a little bit later. But yeah, so what you see here is the grading scheme. Nothing in this course is curved. So if you get a 50% on midterm 1, then that means you earn 50% of the 13% that's available there, right? But at the end of the year, we will curve letter grades, all right? So that means to get an A, it's not going to be the normal 93% that you expect for an A. It's going to be somewhere lower. Last year, it was somewhere between 91 and a 90 to get an A, for example. So the end of the year will be curved, but raw points are not curved, right? Okay. There we go. And a little caveat here is that in order to be eligible to pass this class at all, you must earn 50% of the points in lab. All right, so that means you must show up. All right, that means like you can't just ace everything else and take the L in lab and get an 80%. Nope, we've kind of built that into the system. You must earn 50% of the points in lab to be eligible to pass. So rarely does it happen where someone passes but fails lab. It very, very rarely happens. I think it's only ever happened to me twice, ever. All right, so that means you must earn 500 points in lab, I think, because lab is out of 1,000 points, so FYI. Okay. Calculator policy. I know we're all coming from different walks of life in terms of calculators, but this is our policy for Gen Chem, and it's basically for our exams, you must have one of these TI series calculators, and that's it. So the TI 30, 36, 30 series, the 83, or the 84. All right, those are our only calculators. That means no Casio brands. That means no TI Nspire. That's a common calculator I see. The reason the TI Nspire is not approved is because of the keyboard. What do you have?
I have a TI
84, perfect. So that is approved. There we go, all right? Because I'm not afraid to take someone's calculator at an exam because I show this policy. It's in the syllabus. I have it as a slide. Make sure you check it. And this is just for exams, right? I don't care what calculator you use for online homework. I have no way to check, but this is for exams. But I do urge you to at least practice using the calculator you plan to use, the exam. As kind of a last-ditch effort, our lockdown browser we use to administer exams also has a calculator in it. It's just not very good, right? It's like an iPhone calculator that takes up your whole screen, right? So that's just kind of like a last-ditch thing. Okay, so that's calculator stuff. So lecture/midterm schedule. So here is our schedule of classes. We'll probably deviate from this because I like to talk a lot, and so we might go over, we might go under. So don't worry if we fall ahead or behind on this schedule. We will work through slides sequentially. So if we don't make it to section 1.3, don't worry, we will pick up there on Thursday and we move through everything sequentially. All right, and I'll make sure that we get all the chapter coverage in before our different midterms. But the great thing about this being the only Chem 1250 course is if we don't get to a section for an exam, I can just throw it out. I can just throw it out and put it on the next exam, right? Yeah, that's the great thing. All right, so our exams are outside of class. They're on Mondays. Okay, so we have lecture Tuesday, Thursday. You have labs on different days of the week. But our exams are Monday evening. So do check this against your schedule. And if you do have a conflict, check out our alternative exam policy on the splash page of our Carmen site, and we can arrange for you an alternative if you have time conflicts. And then lastly, if you have SLDS accommodations, in short, it's your responsibility to schedule your own SLDS exams to ensure you get accommodations. We have an SLDS module in Carmen, especially for you, where you see all of that criteria, right? But for the majority of you, 99% of you will be taking exams in these spaces indicated. So you see the chapter coverage, and our final exam is cumulative. It covers all 13 chapters. All right, so there we go. Okay, so online homework. Many of you I saw have already registered for it. Literally, all you have to do is click on any Cengage or online homework link, and it should link you to our course. Because in order to register for this course, you had to pay the Carmen Books fee, and that covered everything for you. So there's no need to take any credit card out for this course except for a lab coat. That's the only thing you need to pay for out of pocket. But online homework, the lab notebook, the lab manual, the textbook, all of that's already paid for. So you get the textbook via online homework. They come together, all right? Okay, so register for online homework. There's links there. And so the typical thing to expect with homework is that there's 1 to 3 sets per chapter. Each set is anywhere from 30 minutes to like an hour long. You don't have to complete an entire set in one sitting. You can save and exit if you wish. And so how we know when homework sets are due is you look for I guess like a red scroll in our lecture slides, and that indicates that homework set is due the following Monday at 6 p.m. All right. So let's say if we finish, if we finish chapter 1 today. Okay, let's just pretend we did. We're not going to, but let's pretend we did. That means whatever scrolls or homework sets that were due for chapter 1 are now due on that following Monday at 6 p.m. All right, so I'll make sure that our Carmen calendar is updated, and I'll make weekly announcements about those due dates. All right, so how to earn points for online homework is you actually have to click submit in order to get points for that homework assignment. So that's why I've broken things up into smaller chunks, because I don't want you to not finish an assignment and not hit submit and miss out on all those points. So that's why they're in smaller sets. So once you finish a homework assignment, you actually have to click submit, all right, before the due date to get those points. So to get points, our online homework is mastery based. That means you can attempt a question as many times as you want. And as long as you get mastery on all of the different questions before hitting submit, then you'll get full credit on that homework set. To put into perspective, I think last year, my online homework grade for 1250 was somewhere like 93%. That was the average homework grade because it's mastery based. Some questions have multiple parts that you have to master before you get full credit for it. So what you want to look for are these M's. Here's an example. Like this homework set has 8 questions, all right? Each of them is worth 1 point. So these M's mean you've already mastered that, you've answered it correctly, you can move on. Note that this question says 2 required. So in this question, there might be 3 questions in the set, but you only need to get 2 right in order to master it. So just FYI, so make sure you read that. Some sets are like, oh, they give you 3 questions, but you only need to master 1. So make sure you're not doing more than you have to earn mastery on a set. So once you get mastery on all the sets, so we get a bunch of M's like this one, you can retry. You can retry again. You reset the question, it'll be a new question, retry it, get that M. If you submit it, then you'll get the total, how many points? Probably 8 points for that homework set, all right? As long as it's before the due date, you'll get that full credit. But as soon as that due date passes, if you hit submit 5 minutes after that due date, it's an automatic 50% penalty, all right? But here's the thing, okay? It's a 50% penalty regardless of how late it is, regardless of how late. So if you wait until the end of the year to do all of the homework, you could, in theory, do that. But you'd only earn 50% of the credit that's possible there, right? So I do urge you to attempt these questions as we go through the chapters so you can get them out of the way and not worry about them later, all right? So here, and if you're getting close to the due date and you don't think you'll finish, I would favor taking the late penalty over submitting an incomplete assignment, because you can still submit an incomplete assignment before the due date, but you only get partial credit. So do weigh those options there. And also I encourage you to use hints and resources to complete these homework assignments. You're not locked, it's not an exam, it's homework. You're free to look up those resources. So yeah, make sure you actually click submit to get the credit. When you click submit, it'll go straight to the Carmen gradebook pretty instantly in our experience. Okay, keep going. Okay, I think I already talked about this, facts about lecture. As you saw from the grading scale, I don't take lecture attendance. I post recordings, all right, they show up. Did I mention that? No, I didn't. On that page, yeah, I forgot to put it there. All right, here's an example. Chapter page. Here's for chapter 5. Let me just go back here. All right. So typically in each of the chapters, each chapter pages, at the bottom, there will be a section called lecture recordings where I put the lecture recordings. Why are there not any lecture recordings there? Because this is the first lecture and we are currently recording. Yeah, so we are recording right now. And so as soon as this class is over and I kick everyone out of my office hours, usually I render the video and I post it on YouTube, and then I embed the video on this page, typically the same day. It's usually one of my wrap-up items before I leave from work. So I do record, but do know that technical issues happen sometimes. Like once I forgot to turn on my microphone and it was just my screen for 80 minutes. So technical issues do happen, but these videos are available to everyone. You don't have to tell me if you're gonna miss class. Please don't tell me if you're just missing one class. I have 1,000 students this year. Yes, I have 1,000 students, all right? So that's why I make these resources available to everybody so you can get caught up with the things that you may have missed, all right? So that is where you will find the lecture recordings. Yes, and then all the additional information there, okay? I get those questions. I've gotten those at the beginning of the year, or it was like the first day of class, and they're like, where's the lecture recordings? I'm like, dude, we didn't have class yet. All right, lab schedule. So as you know, I mentioned there's no lab the first week of classes. So this is going to give you time to get that lab coat in Celeste 108 and register for lab right. There's nothing you really need to prepare for your first lab other than wearing appropriate attire and getting that lab coat. So when you register for lab right, you're going to need your lab section number. So if you go to Buckeye Link and look at this class, so Chemistry 1250, you want to look at the number that's associated with lab, not lecture, All right, you're not going to find the lecture section number. You want your lab section number when you register. So look at your appropriate Buckeye Link schedule. This is just a fake one. But you'll need that to register for the correct section in LabRight. Okay, yes, okay, so facts and tasks for lab. Okay, so you need to register for LabRight using your lab section number. Basically, to register, click on any Van Griner link. So you can click on Cake Chemistry, you can click on the lab manual, and it should take you to the page to register for your lab section. You don't need to pay anything. You don't, if it asks you for a credit card, put it away and try again. You do not have to pay as long as you opted into Carmen Books. You do need to purchase a lab coat. All right, so to buy a lab coat, we're gonna get it from Celeste 180. Do this before your first lab. So Celeste 180 is the building right over there. It's right over there in the back of the building. They take credit card, Buck ID, those things. So you just need a lab coat because goggles will be provided to you by your TAs on that first day. All right, you just need a lab coat. And probably a pen. You need a pen to write with, probably. All right, so make sure in addition to your lab coat and the goggles you get, wear appropriate attire for your first lab. So basically, rule of thumb is any skin below the belt cannot show. All right, so like what I'm wearing is perfect when I have my lab coat on because there's no ankle showing, and that's a common thing that's been happening lately. That's TAs have been kicking students out for ankle showing. So, you know, long pants, closed-toed shoes, and definitely understand those ankles. So, yeah, long, bunched up socks, that's a good thing to bring for lab to protect those ankles. All right, so that's the clothing requirements for lab, and then we have a couple quizzes and the Intro to LabRight Cake Chemistry assignment as well. Those have unlimited attempts with them. So that's something you can be doing this week because we don't have any labs. Right? But other than that, there's nothing really to prepare for VRM. Just get that clothing and make sure that you have all of these assignments completed before your first lab. Okay, so midterms. 3 of them outside of class. I've mentioned that that's where they are. Again, if you have a conflict, fill out our makeup request form. Our midterms, they are not on paper. They're administered by a Carmen quiz under lockdown browser on a device. So it can be a laptop, an iPad, whatever. So one of those devices. I'll have a test quiz for you to test your device out before the exam, all right? A lot of students ask me, you know, oh, do you have to show work on the exam? It's a Carmen quiz, so that means we're limited by multiple choice, pull down menu, numerical response, so no. Okay, you're not graded on your work. We do give you scratch paper and a list of equations, but we do not grade that at all in any way. All right, so it's all multiple choice, so to speak. So I will post the exact copy of the supplemental information you'll get before your first exam. I will post at least 3 or 4 practice exams, at least 3 or 4 in the same style as what you'll get. And I will also have, we'll be having review sessions in lab leading up to the exam as well, and these are for credit. If you check out the lab schedule, but these are over Zoom. Okay, and then finally, the final exam is cumulative. Okay, great. All right, so last thing here, tasks for lecture. You got your tasks for lab, tasks for lecture. Make sure you register for online homework. There is going to be an assignment due on Monday, but it's not going to be a homework assignment, all right? Get 100% on the academic misconduct quiz. This is in your assignments tab. We're very good about putting assignment due dates in our Carmen calendar, so follow that to a T. Do the lab quizzes as well to make sure you unlock that module. And then finally, get a 100% on, this is my syllabus gatekeeper quiz. It's just me to make sure that you understand the expectations of this class. There's unlimited attempts. Once you do it once, just read the feedback and you'll get the answers right there, okay? And then of course, explore our Carmen page. If you have any questions at all before you send me an email, I really highly, highly suggest, because we're all antisocial, I'm assuming. I have a page here Dr. N's frequently asked questions. These are all of the first week of class questions that I've generated from the past 3 years. These are the most common questions I get from students. So most likely the question you have is on this page. Control F, control find. Is your friend here for you to find any question you may have, and with the appropriate links to where to get that answer. So before you send an email, just check if it's on there, but of course I'll answer any question you may have. But probably it's on our Carmen page. We're pretty good with our Carmen pages. All right, and then finally, how do you reach me? I have office hours after class every lecture. So Tuesday and Thursday, just the hour after our class has ended, you can follow me to my office and we can chat more about chemistry. We can talk about engines if you want. I don't have much to contribute, but we can talk about that. Talk about whatever, all right? So the hour after class is yours to have me after class. So just follow me to my office. If too many people start showing up, then we can move it to a classroom. But yeah, it's directly after class. These are informal meetings, informal. Also, to encourage people to come to office hours and to show you that professors aren't scary people, I will give you a small gift to help you on your chemistry journey. It's not extra credit, because there's no extra credit in this class. So if you come to office hours, you will get your gift. Okay, other than office hours, you can email me directly, right here at this email. Don't use Buckeye Mail, don't use Carmen messaging. I hate those. And so if you want a fast response, don't use the things I hate. Yes. And then for security reasons, only send emails from your @OSU. And then also our TAs are very valuable resources. I know you all only have one TA, but you should be able to go to any TA for help, okay? We have 120 chemistry teaching assistants working for us. We all teach chemistry. We're all learning chemistry. Anyone can help you, so you're not limited to just your TA. There are 2 different spaces to get help. The first floor of Celeste has like lecture-like help, while the second floor of Celeste, where your labs are, that's lab-type help. That's probably going to be more useful for you, the lab question help. That's on the second floor of Celeste, that they can help you with any lab question you may have. And the links for times will be right there, all right? And it's during like regular Monday through Friday business hours. And then the lab supervisor email can also reach multiple people, but you can also email me as well. Okay, so that's it. That was long enough, ding. So any questions on how this class is gonna run? Are we excited? Yay, yeah. Okay, we're excited? Okay, do we wanna blow up stuff now or at the end? What do we want? End. Okay, all right, he said it the loudest. Yeah, he said it the loudest. Okay, this class ends at what? 3 what? 40? Ugh, jeez. Okay, so let's get started. Chapter 1. Yes. Okay. Okay, chapter 1. Okay. So some things to note about my lecture slides. So these are the exact same slides that you have. Sometimes I have things pre-written in, but I try to make it obvious of what those are, those filled in slides. So hopefully I'll give you enough time to write those definitions down. But for the most part, it's my philosophy, you know, if I ask you guys to do something, like show your work, I will always show my work too. So up here, when I'm up here with my iPad, I show every single step, I show every single unit, but I expect you all to do that as well. And so at the beginning of your chemistry career here, when we're doing these unit conversions, super important we write everything down at the beginning. So then later, you know, maybe we can get lazy and take shortcuts. But at the beginning, when we're first learning something, not a good idea to use shortcuts at the beginning. All right. So I typically, at the beginning of the lecture slides, also note in red here things that need to be memorized. So what am I telling you to memorize now? Metric prefixes. So you go find where those are in the lecture slides. I can tell you they are on slide 34. All right, they're on slide 34. It's a good idea to just memorize them now, because when we get to that slide, I'm not going to take, I'm not going to take a whole class to get you to memorize them. Or I'm going to assume you memorize them like right then. So I usually mention this at the beginning of the packet. And then of course, homework sets are due the following Monday as soon as we get to a checkpoint. So that means since we see a scroll, our checkpoint is our intro to OWL. So that's our intro assignment. It should only take you like 20 minutes to do. That one is due on Monday. It's just the intro assignment, all right, for you to explore the online homework. But I don't think chapter 1 will be due. All right, so here are the topics we are covering in chapter 1. There is a total of, I guess, 3 or 4 homework sets. We have that intro assignment, and then we have 4 little sets that pertain to chapter 1. And I'll let you know when each of those are due. We'll find the scroll within there. All right, so let's go. All right, so chemistry. I love chemistry. Okay, so chemistry. We often call this branch of science the central science. Right? So it's funny. So we use a different textbook than the rest of the chemistry folks here. We use Chemistry for Engineers. How creative. But the rest of the Gen Chem folks, if you have friends in 1210 or 1220, we use a different textbook. It's called Chemistry, the Central Science. How creative. Right? Because oftentimes folks call chemistry the central science because it just kind of touches on all the other sciences that are out there, and you do see engineering is kind of tangential, especially chemical engineering, material science, chemistry, the study of matter, atoms, and their properties. You can see how that directly relates to material science, and that's why this course, Chemistry 1210 or 1250, is a prereq for material science. Yeah, so you can see that and chemistry centralness, right? So chemistry is the study of matter. What is matter? Matter is anything that has mass and occupies space, right? That may seem like a simple, definition, but it can get kind of tricky. Is an apple matter? Yeah, it has matter. It occupies space. What about air? Is air matter? It is? Okay, yeah, you might be, that one's a little bit more of a thinker, Air, yeah, it occupies space, there's volume there. What about love? Is love matter? No. So my trick to figure out if something's matter or not is if you can put it in a jar, it's matter, okay? Can you put air in a jar? Yeah, you can, and so that is matter. Can you put love in a jar? No, you can't. You can't keep it there. What about light? Light. Is light matter? See, tricky. Technically not, right? Because you can't keep light in a jar, all right? Light doesn't have mass. It's actually just part of the electromagnetic spectrum, right? So light is not matter, but we're going to talk about light tangentially to some other stuff in a little bit. Okay, so one of the reasons I love chemistry is this whole idea, and this is what I call my secret to chemistry, and I will emphasize this over and over and over, because it's what I think what makes chemistry so interesting, is that the composition and the structure of the substance you're working with, all right, on like a particle level, composition and structure dictates the chemical properties that we see. All right, so most engineers care about what properties we see. How can I use this thing to accomplish X, Y, Z? But what chemists care about is what is that thing made out of, right? What particles is that thing made out of that accomplishes X, Y, Z? All right, and so that's the difference here. We're thinking about composition and structure. When I say composition, I mean what atoms are present. Are there metals? Are there non-metals? Whatever. And then this one's subtle, structure. Structure is how are those atoms actually bonded to one another? How are they connected? Because that makes all of the difference, right? It's composition and structure dictates chemical properties, and I think that's a beautiful thing. And we'll talk about that in a little bit, okay? And I'll kind of expand on that difference. Right, so as chemists, I think one of the reasons people hate chemistry or think that chemistry is super difficult, I think the reason is because of this. When using and thinking about chemistry, in this topic, in this study area, is that we are operating in 3 different domains all the time and interchanging them all the time. And so what I mean by domains is we think about the macroscopic domain, the things we can see, right? Think about what water looks like. Are you imagining that? Do you know what water looks like? Okay, now put a cup of salt water next to it. Does it look any different? Salt water, water, salt water. Just by looking at water versus salt water, can you tell a difference between those 2 things? No. So both of those things, they actually are similar in the macroscopic domain. They look the same to our eyes. These are the things we can sense with our senses, the properties we can measure. But as chemists, we care also about the microscopic domain. So the how the particles behave on the particle level, right? What's the composition? What's the structure? That's where the particle domain is important here, all right? So, or this microscopic domain. This is too small to be seen. This is the realm of atoms. We can't actually see atoms or electrons. We can only imagine what they look like. When we draw structures like this, all right, we're actually not super sure ethanol looks like this. I know for a fact ethanol looks like this because I took a picture of it, but this picture representation is just what I think is what ethanol represents. So that is our microscopic domain. But both of these things mean or trying to represent the same thing, an ethanol sample. And then finally, the symbolic domain. This is our language that chemists use to write chemical symbols and chemical equations on paper. All right, so we can use symbols to represent all of these same things. So there's 3 different domains we're constantly working with, but they all refer to the same thing. So really, what I think chemistry is like learning 3 languages at once. We have to relate the formulas, the symbols, to what they mean on a particle level, to what that means on a macroscopic level, what our eyeballs can see. And that's why it's really difficult. So hopefully I can be your guide to navigate you through all of this. Okay, so chemistry, cool. I just like to show this map. I think it's really cool. I put it on our chapter 1 page. I actually just printed it out too. I learned that you can use any of those plotter printers. It doesn't cost that much to print it. So I printed it for $5. They also have map of engineering and map of math. So I'm going to print those ones too and put it outside my office. But what I like here is that there's a lot of different topics. All the things that we're going to learn in this class are here on this green side, all right? So this is what you have to look forward to. We're going to learn the rules of chemistry. And kind of hopefully at the end of the semester, we'll be able to apply these things to actual areas of chemistry that are meaningful and that we care more about. Personally, I am an inorganic chemist, all right? There's lots of different branches of chemistry: organic chemistry, biochemistry. That's the chemistry of the living. I don't like living things. So I'm an inorganic chemist. I like metals, okay? I'm not a real big fan of biology. So I'm an inorganic chemist, all right? I like colors and all of that. So, but we gotta unfortunately learn the rules of chemistry first before the rest of the areas and applications start to make sense. All right, so you have a link to this. I should get on printing those other things. Okay, so let's think about those domains of chemistry in this picture and think about what's happening. So this picture, what do we see? What's happening here? Water boiling, yeah, so water is boiling in this picture. So what domain is that are we using? When we observed it, yes, but what domain word that we just learned? Macroscopic, yeah, we're using our eyeballs to detect what's happening, right? So we note, okay, water is boiling, but you know, if you want to communicate this to another chemist, you might want to write it this way, all right? H2O liquid going to H2O gas. This is our symbolic domain, right? But it means the exact same thing of what I just said, water boiling. Also represented as water liquid to gas is another way we can represent it, all right? Or we can represent it in a particle manner. That water boiling is going from a liquid to a gas, so I can use particles to represent this. In the liquid phase, the water particles, they're close together. But in the gas phase, those particles, the same particles, they're just far apart. All right, so we're using all of the domains in something that is just as simple as boiling water. One other chemical reaction's happening here, and so I will point out turning water to a liquid to a gas. That is called a physical change. Versus this reaction, all right, this reaction is the combustion of methane, all right? This is a chemical change. So this is also using the symbolic domain to represent something that's going on, but it's different. One of them is a physical change, one of them is a chemical change. And I think I have that on the next slide here, differentiating them, yeah. So a physical change, oftentimes we relate this to changes of phase. So if I take liquid water and I freeze it, what do I get? Frozen water, but the people on the street, we call that ice. Yes, so water, turn it to ice. So if I turn liquid water to solid water, ice, is it still water? Yeah, it is. It's still water. So this is a physical change. Physical changes are often reversible because once I turn liquid water to ice, can I change it back to liquid water? Yep, I can. Yes, I can. So those are all physical changes. Physical changes, you do not change the identity of the thing. It's still H2O in both liquid form, in ice form, in steam form, it's still H2O. It's just the phase is different. So we're not changing the identity of the sample. So here's an example, turning ice to liquid to gaseous water. Really all we're doing in a physical change is we just change the internal energy of the sample. That's it. It's still H2O in all of those examples, right? Versus chemical changes are different, and those are fun, more fun. A chemical change is a change that does change the identity of the substance. These are chemical reactions, all right? So in this example, we are changing the identity of the things that are here. So in this example, I'm taking O2, reacting it with H2, and making H2O. So we're taking two different substances, making a different substance with a different formula. So that's a chemical change. So if we go back to this picture, the boiling of water, that's a physical change, but the combustion of methane is a chemical change, but we can represent both of them with chemical formulas and equations. Okay. All right, so let's play the game. Is this physical or chemical? So the trick is physical things. You can ask yourself, is it still that thing? Or you can ask yourself, can you revert it back? So the first one, cutting a banana into slices. Physical, yeah, because what question did you ask yourself? Is it still a banana? And it is, right? Even if you cut it to slices. Okay, melting down a gold chain. Physical, yeah, because melting is just solid to liquids like melting ice. Burning a wood log. Chemical, yeah, because once you burn that wood log, you've spent your fuel. You get ash, and there's nothing left. You can't continue burning it. All right. Turning a wood log into sawdust. That is physical. It's like cutting a banana. Crushing a soda can. Physical. Okay. These are some tougher ones. Dissolving sugar in hot water. It is physical. Why do you think it's physical?
Boil the water, leave the sugar, and water steam.
Okay. Yeah. So you're asking, can I undo it? Right? So when you dissolve the sugar in water, you get sugar water, but you can undo it easily by boiling the water off into steam, and then you get the sugar back. So it's reversible in that way. Like we said, melting and freezing ice is reversible. Yes, that is a tricky one, but you got it. You didn't get tricked. This one is physical. Dissolving sugar in water is physical because it's reversible. But what about this? Caramelizing white sugar in a hot pan. That one is chemical. Yeah, if you know anything about making caramels, maybe. I watch a lot of the Food Network. That one is a chemical change, yes, because you're chemically changing the identity of that white sugar to a nice, delicious brown sugar where it's caramelized. And it's not reversible there. There's no amount of cooking for you to undo it. Okay, cutting my hair. Physical, okay. Growing my hair. What do we think? Oh, I hear some physicals, but it is chemical. Yes, it is chemical. Oh, you guys weren't tricked. Because a lot of folks, they think, oh, cutting the hair and growing the hair, it's like opposite of one another. But how is growing hair a chemical change? And I asked my 1210 students, I go, where does hair come from? And they get all flustered. Where does hair come from? Are we just like these big Play-Doh things that you squeeze on it and the hair comes out? No, where does hair come from? Proteins, where do we get proteins? Or in keratin. Where does it come from? Does it just conjure from the air? Body processes. From the foods we eat. We nourish our bodies. We change the foods we eat to us growing. You know, our parents, they say, eat your vegetables so you can grow because it's a chemical process. Okay. Very good. Wow, you guys weren't tricked. You guys are good. Okay, closely related to all of these properties of matter, physical properties versus chemical properties. This is just a detail of language. Physical properties, these are properties that we can measure without changing the identity of our thing. So typically we observe these things like mass, color, density, temperature. We can measure all of these things without destroying our sample, essentially, right? You can measure all these things, determined without changing the identity of the substance. Versus chemical change, this usually describes reactivity, all right? Like I can say a banana is yellow. That's a physical property. I can measure that without destroying the banana. But if I tell you that a banana oxidizes with time, that property, the oxidation of a banana, is irreversible. So that's a chemical change because that banana oxidizes, it changes from one thing to another over time. So very similar to physical and chemical change. So the big idea here, it describes reactivity. Reactivity. Okay. Okay, so how much time do we have? 15 minutes, okay. Classification of matter. So we gotta, in order to study matter, we need to be able to classify matter, put them in little boxes so we can study them easier. So we're going to be studying different states of matter, solid, liquid, gas. There is a fourth state of matter, plasma, but we're not going to talk about that. Plasmas are just really, really energetic gases where the ions just separate. But a gas, the normal gas samples we'll talk about are just neutral in charge. All right, okay. So, okay, types of matter. We can classify them as two main branches, pure substances or mixture. All right, and of pure substances, there's two kinds. Of mixtures, there's another two kinds. Okay, here is my tip, all right, to classify whether something's a pure substance or mixture. Okay, a pure substance can be represented with a single formula. One formula, that's it, water. What symbol or formula do we use for water? H2O. That's one chemical formula. So water is a pure substance. A mixture, on the other hand, must be represented by two or more chemical formulas or symbols. All right, so two or more symbols. Two or more. All right, so the example I like to give is salt water. All right, salt water is made up of what? Salt and water. So I'm going to say NaCl, that's salt. Okay, and water, which we represent as H2O, liquid. Okay, so NaCl, just salt, table salt, is what? A pure substance or mixture, just table salt. It's a mixture? It is a pure substance because NaCl is just one formula. I'm able to represent salt with one formula and that's it. So it's a pure substance. Water, also a pure substance on its own, just pure water because I can use one symbol, one formula to represent it. But now if I ask you, what is salt water? Salt water is what? A pure substance or a mixture. It's a mixture because there's two things present. What are the things present? Salt and water. But how many formulas did you use to represent that? Two of them. So that's the big difference. All pure substances, you can use one formula. That's it. But any mixture has to have two or more present. All right, so let's talk about different types of pure substances. There's two kinds, two ways we can represent a pure substance, and that's through an element or a compound. So an element, elements on the periodic table, right? So all of these elements, it's just one symbol. So you can represent any of those elements and say, oh yeah, that's a pure substance if it's just one element written. All right, so what you need to know about elements is that these are the simplest building blocks. Once you split an atom of an element even further, that's where you get subatomic particles, all right? And then that becomes physics. So once we start splitting atoms, we leave the chemistry realm. So we're gonna just stop at atoms and say that to chemists is the simplest building block, all right? So the question I always get is, do I get the periodic table on exams? Yes, you do, but it's not completely filled out. It has the element symbols, the numbers, the molar masses. There are just no names. That's it. Okay? So actually the periodic table you see right here in the classroom, that's exactly what you'll get. If you look closely, there's symbols, there's atomic numbers, there's molar masses, but there's no names. So the rule is here is that you need to be responsible for knowing the name, just the spelling of the name of the first 56 elements, plus some common ones, platinum, gold, and lead. All right, so those are just the spelling. And like if I say C, you need to know that element is carbon, all right? So you don't need to know any of the other information, all right? If I say carbon, you should know that is C on the periodic table, and then you can gather, oh, that's atomic number of 6, molar mass of 12.01, and et cetera, all right? So these are our simplest building blocks. Okay, so what makes an element different from a compound? A compound is the combination of any two elements, two or more, on our periodic table. So oxygen, O2 gas, that's an element. That's an element, O2, because that oxygen occurs diatomic in nature, so that is an element. But once we start combining different elements like CO2, now we've combined carbon and oxygen. So now that we have different elements in the same pure substance, now it's a compound. And so that's the big difference there, right? So here are some examples, all right? In this example, all of the atoms are the exact same. We could say, oh, this is a sample of gold or something. I don't know, I just made that up. This sample, we have sodiums and chlorides bonded to one another, so that's a sodium chloride salt compound. And then here's water, because oxygens and hydrogens are bonded to one another, so that is water. So there are our compounds where these compounds have elements chemically bonded to one another. They're chemically bonded. That's different than having a mixture of O2 and N2. The air that you and I breathe is mostly nitrogen and oxygen gas, but those aren't chemically bonded. That's a mixture of elements versus in a compound, these carbons and oxygens are actually bonded to one another. So that's the big difference. Okay, so atoms versus molecules. So I try to be careful with my language. When I mean atom, all right, I'm talking about a single particle of one element. All right, a molecule can mean any two or more atoms that are connected to one another. All right, so it's like an atom is a single Lego piece. A molecule is two or more Lego pieces connected to one another. All right, where in a molecule, those Lego pieces that you connect to one another, they can either be the same element or different elements. It doesn't matter. All right? So this is kind of an interesting thing because we can have elements that are atoms. We can have elements that are molecules. So for example, oxygen atom is just O because it's representing one oxygen Lego piece. But O does not exist in our world. Oxygen, the oxygen you and I breathe, is actually O2. Where oxygen is bonded to another oxygen. This is an oxygen molecule, right? But oxygen, aren't both of those elements? Okay, so we can have elements that can be atoms or molecules. And so it's kind of this idea that all squares are rectangles, but not all rectangles are squares type of thing. So because compounds always are combining two elements, so all compounds are molecules, but not all molecules are compounds because we have some molecules that are actually elements. So here are some examples. CO2 is a compound because there's more than one element, but it's also a molecule because there's more than one thing bonded to one another. Nitrogen, this is an element because you can find it on the periodic table and that's it. But this is also a molecule because there's two nitrogen atoms bonded to one another. Helium, on the other hand, that's an atom because it's just one thing represented there, but it's an element. And so we just have to be really careful with our language there. So let's see if we can't do this and recognize these different examples. Are we looking at a molecule or an atom, or are we looking at an element and a compound, or a compound? So this first one, CH4 or methane, is it a molecule or an atom? Molecule, how do we know? What are we looking for? Stuff bonded to one another, yeah. C's are bonded to H's. Okay, but is it an element or a compound? Compound, because there's both carbons and hydrogens. Perfect. Neon, what is that? Atom, because it's one thing, and then it is a element. All atoms are elements here. O2, molecule. So what makes oxygen different than neon here? Two, perfect. Yeah, the two oxygens are bonded, and then what is this? Element. Yeah, because oxygen is on the periodic table. Okay, SO2, molecule and compound. S6, molecule and element. Perfect, great. Okay, these are my favorite slides. Okay, so the secret to chemistry, I already told you. Properties are determined by composition and structure. Composition means what atoms are present in the molecule you're forming. Okay, so like what elements, what Lego pieces did you pick? Structure means how did you put them together? How did you put them together? So how did you build your little Lego pieces? And so both of those ideas are really important in predicting properties. Okay, and so as a material scientist, I think it's super important to make that connection that, you know, the elements you pick on the periodic table is not the only factor, but it's how they arrange themselves in 3 dimensions, dictate those properties that we see. So here's a cool example. Here are 3 molecules. All of them have the same formula, C3H8O. So they share what? The same composition or structure? Composition. So what I'm going to differ here in these structures are on their structures. So they all have the same Lego pieces, but if you look closely where the oxygen is, the red atom, they're in different places here. All right? So I took the same exact Lego pieces. We all have the same Lego set. We just built different things with them. And what we get out of this are crazy different boiling point temperatures. All right? So one propanol has a boiling point temperature of pretty close to where water boils. You got to heat it up a lot. All right? Once you put that oxygen atom in the middle of the molecule, it lowers it to 82. So it gets a little easier to boil it. Put that oxygen in the very middle of the molecule, and this substance is already boiling at room temperature. All right? So here's an example where we can have 3 things with the same composition, different structure, wildly different properties. Do you think that's cool? Yeah, don't humor me. I think that's actually pretty boring, all right? 3 different boiling points, okay. So here's another example. Here are 2 molecules, cisplatin and transplatin. So look at both of them. There's both of them have a platinum atom. Both of them have chlorine groups, right? And then both of them have these NH3 groups. All right, so their composition's what? The same or different? Same, perfect. But what about their structure? They are different. See how one of them, the chlorines, they're trans to one another? And then the other one, the chlorines, are cis to one another. To remember, I think cis, they're sisters, they like each other. So what I imagine sisters would do. All right, so they're next to one another, right? So we see the structures of these 2 molecules are different. One of these molecules is the #1 chemotherapy drug on the market, and that's cisplatin. The 2 chlorine atoms are at a perfect geometry to cross-link with fast replicating DNA. What does fast replicating DNA sound like? A tumor, yeah, cancer, all right? And so cisplatin links up perfectly with RNA strands because of the cis arrangement of the chlorines. Transplatin does nothing. All right, so here's another example where composition is the same, structure is different. One of them kills cancer, the other one does nothing. All right, and so again, highlights the interesting properties, ideas that chemistry not only study of matter, but us relating, okay, composition and structure dictate these properties. I think that's cool. Do you think that one's cooler? Yeah, Cancer, cool. Okay, here's my last one. I think this is really cool. All right, diamonds and body armor. Do you think they're related? They are related. Yeah, because I'm teaching you that they're related, right? Okay, diamonds. Diamonds, they are made up of pure carbon, just carbon atoms in this tetrahedral environment. This is their crystal structure, all right? So diamonds, they're pure carbon. Oh, I forgot, I had to look up the cost of these, but I forgot. So diamonds are pure carbon. What else out there is pure carbon? Oh yeah, I guess you can just look at the slide. Pencil lead, graphite, also pure carbon. So if we compare these two things, diamond and graphite, their composition is the same. But if you look at their structures, diamond, each of these carbon atoms has 4 other carbon atoms attached to it, but graphite has these parallel sheets to it. And that's how we get wildly different properties. So we see that diamond and graphite, are their properties similar or different? I think diamonds and graphite are different. They look very, very different, and we achieved that by just changing the structure a little bit, all right? Okay, so that's diamonds and graphite. So let's look at diamonds to a common diamond alternative, moissanite. So me, I'm a millennial. So what do we do? We destroy the economy. We eat avocado toast. And we don't buy diamonds. And that's true, I do not buy diamonds. My engagement ring, I chose it. I picked it myself. It's made of moissanite, and I'll show you why, and it's via this slide. And there's a cool gemstone, it's called alexandrite. Yeah, you can talk about in office hours if you want. So anyway, diamond to moissanite. So tell me, just using your macroscopic domain, how do these properties, are these similar? Do these have similar properties? Yeah, I would say so, these two gemstones, diamond versus moissanite. But let's look at the composition. Here, diamond is just carbon. Moissanite is silicon carbide, where we take half of the carbon atoms in diamond and we replace them with silicon. Look at where silicon is on the periodic table. It's right under carbon. So we're essentially just replacing half of the carbon atoms in diamond with its big brother, silicon. So we're changing the composition, but just a little bit, all right? We're just changing it a little bit, all right? And so what we see, composition is different, but what ends up happening is that the structure is similar. We can look at the centers of some of these unit cells, and we still see we have this tetrahedron crystal structure. And so what happens is that we end up getting very similar properties. All right? So ethically, I do not buy diamonds for ethical reasons, but also for chemical reasons. Okay? So I think I looked it up last year. The numbers are probably still the same. If you wanted to buy a 2-carat diamond, that's pretty big. All right? I think that's like 8 millimeters across. It's pretty big. Okay, an 8-carat diamond, like the worst quality one you could buy is about $10,000, all right, for a 2-carat diamond. Okay, but a 2-carat moissanite lab-created gemstone, it's $1,000, all right, it's $1,000. So that's much more reasonable, okay? But a lot of people are like, well, why not cubic zirconia? Cubic zirconia is actually made up of a metal and a non-metal, so cubic zirconia is actually an ionic compound. So ethically, I want to keep true to these network covalent compounds. But anyway, diamond, moissanite, different composition, similar structure. Okay, so how do we get to body armor? Okay, so moissanite is silicon carbide. Body armor, trademarked by Saint-Gobain, is alpha silicon carbide. All right, so body armor is just pleated sheets of half silicon, half carbon atoms, but they're in sheets, all right, I guess in this alpha arrangement. And so we see, yes, we get absolutely different structure, different properties here when we go to moissanite to body armor, but we see, oh, the composition stayed the same, but now the structure is different. The structure of body armor is similar to that of, just look up with your eyeballs, is similar to that of graphite. All right, so you see here that we have this similar layering of graphite and body armor, and this is how this whole chart comes together. All right, we got 2 carbons on the top, silicon carbides on the bottom, so we just replace half of those carbon atoms with silicon. We have a tetrahedron crystal structure on one side, we have a layered structure on the other side, and we get this vast array of chemical properties. Some gemstones, some tank armor. All right, and I think that's cool. Do you think that's cool? Or do you think the cancer one was cooler? Okay. This one's very comprehensive, okay? It's very comprehensive. Okay, what do I have, 10 more minutes? Oh yeah, we can finish these slides. Okay, so composition and structure dictate chemical properties. That's the moral of the story, and that's how I like to start these classes. All right, so we talked about pure substances, elements, and compounds, so let's talk about mixtures now. We have 2 types, heterogeneous, homogeneous. For the most part, as scientists, we're going to study homogeneous mixtures. Homogeneous mixtures are uniform, and these can be tricky because homogeneous mixtures oftentimes look like pure substances because they're uniform. But on the particle level, you do see the presence of different things. Like I asked you, what does water look like? And then I can ask you, what does salt water look like? Don't they look the exact same? All right, but on a particle level, water is a pure substance. Salt water is a mixture, specifically a homogeneous mixture, a solution, because salt and water are present. All right, versus heterogeneous mixtures, typically there's different phases. They're a lot easier to discern. Like here in this example, you see different like globs of different atoms. In the homogeneous mixture, you can see this could be like salt water. The salt particles are distributed evenly throughout the whole thing. All right, so homogeneous mixtures are also called solutions. All right, solutions. All right, but oftentimes I will abbreviate solution like this. So if you see me write this, SLO with an N to like a exponent for some reason, that means solution. I don't know why I do that. Homogeneous mixture and solution, they're synonyms for one another. But this is what commonly happens. Students, they understand, they're like, yeah, salt water, that's a mixture, or that's a solution. That makes sense, salt water. But oftentimes, the thought is, oh, a solution has to be a liquid, but that's not true. As long as it fits the criteria of being uniform, having more than 2 components not chemically bonded together, then it's still a solution. The air that we breathe, all right, is composed of nitrogen gas, oxygen gas, CO2 gas. Is the air we breathe uniform in composition? Is the air I'm breathing the same as the air you're breathing? I hope so, yes. So air is uniform, so it is also a homogeneous mixture. But then I ask this exam question, and I ask, is air a solution, true or false? What is it? True, it is true. But what's the trick there? What's the trap students fall into? Yeah, so oftentimes students think, oh, solution has to be a liquid. That's not true. Solution just means homogeneous mixture, and in this case, it happens to be the gas phase. But we can have it in any phase. Any alloy you work with is also a solution, all right? 14 karat gold, brass, bronze, all those things, mixtures of different elements, those are also technically solutions as well in the solid phase. Okay. So let's finish these couple slides and then blow stuff up. Okay, so here is a nice flow chart to help you determine whether something's a pure substance, element, compound, or is it a mixture, homogeneous, heterogeneous, all right? Based upon properties, okay? So those are the types. This is kind of the order in which we learned them. I like this chart for some reason. I just think, okay, pure mixtures, 1 formula, here are the different kinds, mixtures, 2 formulas or more, here are the different kinds. Or you can think about it from like an observation standpoint. Ask yourself, is it uniform throughout? If it's uniform, you could either have a pure substance or a solution. Remember, because we said salt water and water look the exact same, but what's different is on the particle level what's present. All right, so that can help you with your studies there. All right, the last slide we'll work on here is let's put it all together, our definitions. Let's match the following. Of these 4 pictures, which one represents a molecule of a compound? What do we think? Molecule of a compound. Oh, I don't want to do it this way. Let's do it. Let's work left to right. Yeah. Okay. So tell me, this picture represents what? A, B, C, or D? That's how I want to do. D. Yes. Atom of an element. We know it's an atom. What's the giveaway? Just one ball. Yes. And so if it's one ball, it's an atom. It has to be an element off that periodic table. Okay. What about this guy? C. Yes, this is molecules of an element. So C and D, those ones are commonly mistaken. Atom, one ball, versus molecule, more than one atom bonded together. All right? So it is an element. It's implied it's an element because there's one color. Okay, all blue balls, all red balls, one element present. Okay, what is the next one? A, yeah, so molecules of a compound. So this compound could have a formula like MX3. The purple atom is M, and then the 3 green atoms are the X's, for example, right? So that's one formula. So then the last one. What is the last one? B, yes, the last one is B. It is a mixture. So of these 4, which ones are pure substances? Is the first one a pure substance? Yes. How about the second one? How about the third one? Wait. What's the trick for pure substances? You can represent it using one formula. So let's just practice this. The first one, we could represent it with the formula, I don't know, what could it be? It could be neon, right? Neon. What about the second one? That could be like, not xenon because it doesn't become diatomic. It could be like oxygen gas, O2, 2 oxygens bonded together. But what did I write? MX3. That's one formula, right? So the third one is actually a pure substance too. Remember, there's 2 kinds of pure substances. Elements and compounds. So neon is a pure substance. Water is a pure substance as well. All right? And then B is the only one that's not. All right, so let's look at these pictures and again do the same thing. Are these things a pure substance or a mixture? All right, and I give you, note the formulas and all the information I give you. Aluminum oxide, pure substance or mixture? Pure substance. How do we know? One formula, yes. Okay, so if it's a pure substance, is it an element or compound? Compound, yes. So we don't have to do the mixture one because it's not a mixture. All right, the next one, just aluminum. Pure or mixture? Pure, element or compound? Element, okay, don't have to do the mixture. All right, the last one, 14 karat gold. It looks like there's 80 or 58% gold, 41% silver. What is it? It's a mixture. How do you know? You use 2 formulas. Yeah, there's gold and there's the other thing, silver. Yeah, so I had to use 2 formulas, so it's a mixture. But this one's tricky. So now it's this one. Okay? If it's a mixture, is it homogeneous or is it heterogeneous? It is homogeneous, yes. It is homogeneous. Because if you just think about 14 karat gold, yes, it should be gold, that quality uniformly. Oh, I can't just put H. I have to put homo within there. All right? Okay. And so I just want to point out like the big difference between aluminum oxide and the gold, why 14 karat gold is a mixture. Is this gold silver analysis, is this a formula? No, it's percentages. I'm just telling you I threw in this much gold, this much silver. So that is just a mixture. They're not actually chemically combined. Okay, so we got 2 minutes. So let's blow some stuff up. So my goal is to blow as much stuff up as possible in this class. Because, well, here's the thing. I was given the unfortunate task of possibly being your only chemistry experience ever in college. So of course I want you to have a positive chemistry experience. And if that means blowing a lot of stuff up, then that's okay. So I just do want to teach you proper blowing stuff up etiquette, okay? So what I have on here is not just a lab coat, but it is a fireproof lab coat. I really should have my hair up, but to practice proper safety and to show you that I am serious about safety, I'm gonna give you this fire extinguisher just in case something happens, all right? So it's right there for you to use. Okay, so this can be quite loud, so I am gonna ask everyone cover their ears. If you want a deeper experience, actually do Dumbo ears and like cup your ears like this so you can still hear behind you. It's a nice experience when you do that. Okay, I don't know how this will go. We'll see. It's been loud in the past. We can always try again on Thursday. All right, so let's start this semester with the bang. So let's see. Ooh. That wasn't even that loud. You guys. We ran out of oxygen gas. Okay, let's see what this one's like. Ears, ears. Yes, everyone, ears, ears. Okay. Ooh. That one was supposed to be a color. Did you see what color it was?
Red.
I don't know. Okay, all right. A last question. Was that a chemical change or a physical change? That was a chemical change. All right. Okay. I'll see you on Thursday. Oh, come to office hours.